I'm up and ready. Not quite sure if the audience is up and ready. Looks pretty sparse out there. But glad for those of you in the audience. It will be an awesome talk. Glad you could make it. So I'll be speaking today about botnets, DDoS, and GroundTruth. And despite the title, let me just pause to just do some expectation setting. Much as I like to make broad, sweeping statements about Internet and how the Internet's changing and about security, this talk really is about a fairly small study, and it really is very preliminary results. So I'm not quite going to extend the talk to make claims about security Internet-wide, but there is some interesting, I think, anecdotal data that I'll be going through today that we've been collecting over the last year. So first, a word about GroundTruth. You know, in the academic world, you hear GroundTruth come up all the time in papers. And for academics, GroundTruth really is a difference between their models and their simulations and, for lack of a better word, reality, what's really happening. It's where their models and their simulations meet what's happening in real networks, real computers, real environments. And it turns out GroundTruth is the holy grail, and GroundTruth is really, really hard to obtain, especially in areas like security. You know, certainly in enterprise security, understanding what's impacting enterprises, what security events is hard, but it gets even more difficult when you talk about national communication infrastructure and critical national infrastructure. And, you know, from survey data and other things that we've looked at, it's pretty clear that a vanishingly small number of providers actually report attacks. You know, only 5% or less actually report some of the DDoS or botnet attacks they've had last year. With that said, there's absolutely no shortage of surveys. Cisco does surveys, Arbor does surveys, there's dozens and dozens of vendors and analysts doing surveys on security data, on security trend. But there really is very little hard data, very little quantitative data. And in fact, I think as Danny and I have experienced, when we do these vendor surveys, we often ask questions like, what is the largest size of the botnet a given carrier has experienced? And, you know, the numbers come back in all over the place, from hundreds of thousands to millions to tens of millions. And it's quite clear when you actually go back and talk to any of the carriers about where they're coming up with their numbers. While many of them, I'm sure, have good sources of data, it's pretty clear a number of them are just making it up as they go along, that, you know, these numbers are hard to come by, particularly when you get into things like botnets and zombies and so on. There's also no shortage of research papers. We're now on to, give or take, about 100, 125 plus academic research papers published about DDoS mitigation, DDoS detection, all arguing why a given paper this year, 2 were published this year, it turns out, were better than the algorithm last year. And it's kind of fun. If you go back and you read the paper this year, they argue about they have better detection, better mitigation, and we have 10% better efficiency than the paper last year. You go back, read the paper last year, they had 5% better than the year before, and you keep going back, and eventually you find out the original data source is synthetic. They made it up. So you go back 5 or 6 years to the original data source, and someone, when they were asked to write a paper, they decided, this is what I think anomalies look like, this is what DDoS looks like, and then you've got these entire ecosystems of papers that develop through the years. So again, very challenging for academics and for operators to actually have ground truth, to know what do attacks look like, how do you characterize them, and how are they evolving. And of course, the key challenge when you do anomaly detection in carrier networks or enterprise networks, it's always differentiating the false positives from the true attacks. You know, anomaly detection is easy. Validating anomalies is hard, and knowing that if they are false positives or true anomalies is the really tricky bit. So this talk again, we're going back to Atlas data. But unlike the talk I gave last time where we were focused on traffic data, this one is focused on security data. And in particular, about 2 years ago, we added the ability to manually classify events within some of the Arbor products. And over the last about year and a half, we've actually had a number of operators start to make use of the workflow and manually classify if events were false positives, true attacks, and so on. So slowly accumulating a data set. So today the talk's about covering 37, give or take, ISPs of the last 12 months. And we really have two different overlapping data sets. One is attack data, where we actually have anomalies that were detected and then manually classified. And then we've got a smaller data set where we've got data on mitigations, where actually an event was detected either via the system or a mitigation was manually created, and then we track statistics associated with that mitigation. So we're now up to about, give or take, 5,000 events that we have that were either mitigated or that were manually classified as an operator as a real attack. And I'll be going through that data in the remainder of this talk. So just a quick screen snapshot, just to perhaps make it a little more concrete. This is actually what it looks like from the workflow, that when there is an alert, the operator has a choice to classify it as a false positive, flash crowd, trivial, or of course a verified attack. And that's what we really are interested in this talk, is looking at the attacks that are classified as verified. Though of course, flash crowd and possible attack and others are interest of well. And of course our goal in this is both we find this interesting from a research perspective, but we also of course have commercial motives, evaluating the efficacy of our algorithms and mitigation. So hopefully useful for both commercial and research purposes. So before I get into the data, I do need to provide, I think, just a minute of background. One of the things that's hard is that we really have a toolkit now where we're collecting data on a variety of different sort of measurement bases. But much like I imagine physicists sometimes have a problem of inferring actually what they're seeing, each of these tools tells us something slightly different. And you do have to sort of piece many of these together to understand when you're seeing spoofed versus zombie versus other types of attacks. So I'm going to avoid, I think, getting into too much detail about what some of the commercial mitigation hardware does, obviously being sensitive to commercial intellectual property and privacy issues. But I will say most devices like this, including the old Cisco Guard, Arbor's gear, and other vendors, typically the mitigation operates in terms of a number of layers, where you've got each layer allows different levels of traffic through and is catching different types of statistical, behavioral. You have a layer that's detecting things at the IP layer, where some number of unusual source IP behavior, statistically, behaviorally. You've got some botnet behavioral detection, and then you go up the stack with TCP validation, things looking at abnormal types of TCP connections, things like TCP SYNs, SYN floods, all the way up to looking at payload and up the application. Each layer catches slightly different types of attacks and different types of traffic, and the system in the back end is tracking different statistics at each layer. For example, tracking both traffic passed, traffic dropped, source IPs, number of unique IPs, number of unique connections, and so on. And I'll talk more about some of that data in the next couple of slides. So I think when we went into this talk, we were trying to understand sort of the landscape and want to revisit some of the assumptions about DDoS and about botnets. I think generally when I talk to operators, there's three prevailing, I think, conventional wisdom about DDoS today. Number one is spoofing is no longer common. After all, botnets have gotten so large. There's just so many millions and tens of millions and hundreds of millions of compromised hosts out there that if you're actually launching DDoS, you just use a botnet and spoofing is passé. The other claim, of course, is that botnets and DDoS are large, that all of these involve thousands or tens of thousands or hundreds of thousands of hosts. And finally, that most DDoS today is still just brute force flooding. It turns out, as I go through the talk today, that I think two of these claims, or only one of these claims is true, and probably two are actually not true in terms of conventional wisdom. And you'll have to pay attention to the talk to actually find out which is which, but I'll provide some hints as we go through it. So a quick overview of the data. As I mentioned, this is a preliminary study. It really is too small to drive industry-wide conclusions. And the data is pretty varied. We have some data sources which look like they are folks protecting their multi-billion-dollar web properties. We have other carriers who are using this to offer as a service to their T3 customers, and turning up DDoS on a per-demand service basis. So quite a bit of variety in the data. Hard to make very generalized statements about the overall internet. But we do have, I think, a range of data sources, and it does include at least attacks up to 22 gig, 9 million packets per second in the data. Though this is smaller than, I think, the reports we've heard from carriers that have experienced 50, 60, or even larger. So again, fairly small sample size of the attacks we're looking at, but still, I think, a large enough data set to be interesting. Quick look at just drilling down into the data. It turns out that the statement that is true is that most attacks today, if you actually look at the attack data, are actually flooding attacks. Fairly brute force attacks trying to consume either computational or bandwidth resources. About 60% are flooding, followed by TCP level attacks, which generally are smaller, focused on exhausting connection state, either in load balancers or firewalls or on the end system. And then we've got, I think, application at 8%, and policy is when we've got data from folks that are doing things like application level filtering regular expressions, GeoIP filtering, blocking all traffic except from North America or Europe. Some of these are running just constantly, more being used like sort of like an IPS. But again, we've got, give or take 12, 15% that are matching some type of policy enforcement. So here's where the data, I think, gets a little more interesting. This is an overview of the 5,000 attacks we're looking at, breaking it down into 3 columns, megabit, PPS, and duration. Each column, by the way, is independent or calculated independently as we look at the median, average, 95th, and max. I think it turns out that the median is actually quite small. The median is mostly just lots and lots of small websites being attacked on a near constant basis with 30,000, 40,000 kpps SYN or flood attacks. And that really is, it's a very heavy-tailed distribution or long-tailed distribution, but the majority is fairly small. With that said, as you get up towards the right side of the graph, the attacks suddenly get quite big. So when you get to the 95th and max, the data really is skewed by the larger attacks, where you get into the average being 200 kpps with 300 meg attacks. And of course, we get up to the largest attack in the data set, which was 22 gig lasting 4 days, about 9 million packets per second against a single /32. And what was interesting is that they chose, whoever this was, chose to mitigate this attack. I always do wonder why they didn't just BGP, source or dest off-ramp it, but for whatever reason, they had 22 gigs going for 4 days, and they were scrubbing or filtering the traffic. So I'll now dive into a couple of the different layers. And again, we'll start down at the flooding layer, work our way up through TCP, and then up through the application layer. Now, flooding attacks are where we are looking at source behavior, and we're identifying unusual behavior in sources who are sending, behaviorally, statistically, traffic that violates all sorts of different heuristics. And we're tracking the number of IPs involved in the average, PPS, and megabit. And I think the thing that surprised me on this slide is that I really did believe that we'd find hundreds and thousands being common in terms of the size of the sources involved in many of these attacks. And the median and the average are actually quite small. These aren't massive, giant botnets. These are a couple hundred. 30, 60 machines sending, in some cases, well connected, sending multi-meg, 100 kpps, but relatively few sources involved. And the other thing that becomes clear as you look at the data, that there's some source data that clearly is unrealistic. When you get to averages of 4 gigabits for the same source IP, or averaging 4 gigabits and 1 million PPS for a source IP, it does tend to suggest one of 2 things, or maybe 3 things. It suggests that either they're spoofing, and they're doing a really, really bad job of spoofing, that you've got lots of tools just using the same IP. So you've got a great botnet, and then you're using the same IP in your spoofing tool. It suggests maybe that you've got a large, mega proxy, large NAT, or something else happening. But about 10% of the attacks just don't make sense in terms of the source traffic. I tend to suspect this is mostly bad tools with really bad, bad spoofing going on. And I think the spoofing becomes a little bit more clear on the next slide. This is traffic that's not caught by the zombie layer, that's not caught by looking at the source traffic. So this isn't just a few sources. This actually needs to be fairly well distributed. And on this slide, we're looking at the connections per second, the number of TCP connections attempted per second going to a given victim during given mitigation. And then we're looking at the number of hosts that actually pass the different sorts of hurdles we put in the way to validate that they really are legitimate hosts. And it's kind of interesting. Get to 3 or 4 or 5 orders of magnitude difference between the number of connections attempted and the number of valid hosts. It does, again, tend to suggest fairly widespread spoofing or very, incomplete stacks. It's very hard for us to distinguish between really bad implementations or half-completed stacks as part of attack tools or spoofing. But it does tend to suggest spoofing's out there with relatively small number of hosts. And again, it does get up into the millions of connections per second. The next category of stuff is application attacks. So after we're done with zombie, after we're done with TCP and flooding attacks, we've got a growing number of attacks that tend to be fairly low bandwidth, but really focused on very expensive SQL backend operations URL, as well as in the right-hand table, attacks focused on the SBCs, on different types of SIP operations, SIP flooding attacks, and so on. About 8% of the attacks we're seeing today are really focused on the application layer, and that seems to be growing. Particularly HTTP and SIP and DNS tend to be the big ones. I think the differences between HTTP and SIP are kind of interesting. We've got some websites out there that look like they are just under constant attack, 24/7, weeks on end, hours and hours with several hundred or up to 1,000 hosts, all trying to do very expensive get, post, whatever the operation is. SIP, it looks like, tends to be briefer attacks, and as we get into the 100,000 PPS and 300 meg, tends to be more focused on the flooding and more resembles some of the broader flooding attacks. So again, just some, I think, some interesting data points as we're just starting to broaden the data set. It's often hard for us, one of the biggest challenges of having anonymous data is that the data is anonymous. And that's particularly a problem when we want to understand who's actually being attacked and why, what are the motives, and what are the trends. So on this slide, on slide 14, we're just looking at within the attack data when we do have data about the ports and protocols. We don't actually know what the IP addresses were or who the actual target was, but this is a quick breakdown of looking at least from a port protocol basis, what's being attacked. And the largest category is stuff where we just don't know. It's either a flooding attack, where they're just randomizing the source ports and the protocols, or it's a service that includes a broad range of ports and protocols, like many of the games and other servers out there today. But beyond the, I think, broad port range, you get into web is the most popular. IP fragment and DNS all make the top 3 or 4. So basically, I think mostly what you'd expect today in terms of what is under constant attack. I think I found this slide interesting as well. We're looking at not that we know what the actual IP address is, but we do know the prefix length. Most attacks out there, the vast majority, certainly for BGP, where the operator chooses to BGP black hole either the source or dest, the vast majority of these are all for /32s. And by the way, once a /32 is nailed up, it's often there for weeks or even in some cases months. So very large numbers of operators with hundreds or thousands of BGP prefixes that are just off-ramped. And again, this is data that we're seeing if they actually choose to use the Arbor system to do the off-ramp. We're tracking that. When you look at actually traffic that goes through the mitigation device or the TMS, that will actually do payload-based mitigation, it looks like the TMS is used both for /32, about 60%, as well as covering broader infrastructure as there's broader CIDR ranges involved. And typically, by the way, we expect that the much of the /32 reflects load balancing or NAT infrastructure. Just quickly on the duration of the attacks, that this is actually based on mitigation data as well. When you look at when an attack is mitigated, how long is mitigation running? For the vast majority of TMS or the payload-based inspection, it's under an hour. which probably reflects both the nature of the attack as well as more granular control in the mitigation. But if you have a BGP black hole set up for a customer, it's likely there to be there for hours and days and even weeks. And again, we've got some carriers that seem to be running with hundreds, or in one case, thousands of these running in their tables. And we don't know whether these are, unfortunately, we don't know whether these are, again, source black hole or DEST. So with just a couple minutes to spare, I'm on my last slide. This talk, again, I wish I could make broad statements about how attacks are changing based on real data over the last several years, but we've got only a very small snapshot and only 37 carriers. But the data we do have suggests that spoofing is still fairly prevalent. Most attacks actually involve fewer botnets than I would have expected, hundreds of hosts rather than tens of thousands or thousands, that these tend to be well-connected hosts, and that there's growing incidence of sort of service application level attacks. But the real point of this talk actually wasn't any of the above. The real talk was we've got a really interesting data set with very small participation. I think this data could be very useful, and this is as much a call for folks who aren't participating to participate and to enable the anonymous statistics. And with that, I've, I think, 2 or 3 minutes of questions. You're always good for a question, Dave. Thank you.
Dave Meyer. I'm wondering if you could say something about what you think the sophistication, you kind of classified things by sort of mechanism, but do you feel like the attack space or the sort of the source of these attacks is getting more sophisticated? I'll just give one example. Like, the Stuxnet thing, right? That thing is pretty sophisticated. And it was probably built by a, programming team and for, specific purposes. And I'm wondering if we're seeing any of that kind of stuff, or if you can even detect it.
Yeah, I think there's a definite trend towards application-level attacks. I think it's that the industry's matured. It used to be, 7 years ago, a 400 meg attack or a 200,000 PPS, SYN attack would be enough to cause damage. Now most operators have kit in place, whether it be Arbor or other vendors, and the bar is raised. Where as a vendor, I think we see some of the challenges are with the more complex services, where we've got things that are both harder to detect, they're lower bandwidth, and that the attackers clearly have done their homework. That it isn't just by accident that they choose the one post operation that's the most expensive they could have chosen out of the tens of thousands or millions of posts. So there's clearly it's not it's probably the under 5% of the attacks, but the attacks that are getting sophisticated are very there's a long tail, which is folks flooding and folks doing stuff that they've been doing for the last decade. It's fairly easy to remediate. The 5% on the far right is where it's getting interesting. I don't know if we've seen things. I've only read about the some of the Stuxnet. I don't know if we've seen things quite at that level. Everything I've read about it sounds more impressive with each press article I read.
My name is Scott Shepard. I'm with AT&T Labs, and I'm going to freely embarrass myself. I'm kind of new at this. This is a new world to me. And I'm getting very confused on some of the terminology as I learn this, and some of the methods for detection as I learn this. And I assume a few of you here are probably in the same boat I am. Do you have any recommendations or suggested reading or good references or something that maybe could be appended as an appendix to your presentation on introductory methods and tools for detecting these types of attacks? I know how to find some of them, but it would be nice if you're saying, gee, I want to have you folks give me information about attacks. Perhaps there needs to be a more standard methodology of how to detect these attacks, how to classify these attacks, kind of a primer on, this is the project I'm working on. I need this information, it's useful to the community, here's some basic ways to do this that are generally accepted practices? And I know it's a stupid, dumb question, but kind of needs to be asked.
Sure. So, there's a number of books about, I don't know if there's agreed upon terminology. I think it's still sort of an evolving field.
Point.
There's a number of books, and there's certainly a number of papers that attempt to provide a taxonomy. I think what we were really asking for in this is that one of the nice things about some of our deployments, where we've got still a fairly small percentage of carriers participating, is that it does provide a uniform mechanism for measuring like by like and providing that in anonymous statistics. Whereas, in some of the survey data and others where providers are making their own measurements using a variety of tools, it's often very hard to combine the data or analyze the data given the vast disparity in how it's being measured and how it's being defined.
I have one last follow-up. I've read some of those papers, and believe me, I've plowed through some of the terminology, which radically differs from paper to paper. The next thing is, I recognize that you are a corporation. I recognize that most of this is based on your particular proprietary tools. No complaint about that. But if you're trying to do this, what I think is a relatively valuable study, have you reached out to the academics? Have you reached out? I know you've talked about other vendors trying to do surveys and stuff to try to develop a uniform method of survey for the community at large to collaborate on the collection of this information.
I don't think we've done much beyond this effort and the survey we do. I think it would be an interesting effort if it's possible.
Thank you.
Okay, thank you. I think we're done.
Thank you, Fred.